Welcome to the alternating series test. So up until this point in time, all of the series that we have tested have had all positive terms. Now we're going to have series where the terms alternate from being positive to negative. As an example, so let's say we have a series and I graph it and I have a term that is positive. And then the next term is negative. Then the next term is positive. And then negative, then positive, negative, on and on towards infinity. Well, the way that I have drawn this particular alternating series with the alternating positive, negative terms is it is converging. It's converging towards zero, right? And so what we want to do is we want to determine how can we analytically come up with a test that will tell us if this alternating series is actually going to converge or if it's going to diverge. And so that is the alternating series test. And there are two parts to the test. The first part is to take the non-alternating part of this series and call it B sub n. So the part of this series that actually makes it alternate is the power of -1. When -1 is raised to an odd power, it will be negative. When the -1 is raised to an even power, it will be +1. So -1 raised to the second power is 1. -1 raised to the third power is -1, on and on. So that's what causes this to alternate between being positive and negative. So if we just take the alternating part out and we call B sub n 1 over n squared plus 3, let's just see what that series is doing. Right? So what we're going to do is we want to test the series without the -1 part into it. And so we are going to take the limit. This is the first part. We want to take the limit as n approaches infinity of 1 over n squared plus 3. So in other words, we are finding the limit of the sequence. So B sub n is the sequence part of the series. And we want to find the limit of it. Now, if the limit approaches 0, we're good. Okay? If the limit approaches 0, we are on the track towards convergence. So we can see from this that that is going to be true. The highest power of n is n squared. So if we divide everything through by n squared, we are going to have the limit as n approaches infinity of 1 divided by n squared is 0, and so we're going to have 1 plus 0, which is 0. So the limit is approaching 0 when we just look at the positive. So essentially what's happening here is we've taken these negative terms and we've made them positive. We're taking all the negative terms out and making them positive. That's what we're doing when we look at just the 1 over n squared plus 3, ignoring the power of -1. And so we can see from this, when all the terms are positive, that it is converging towards 0. And so that's what we have just showed analytically by taking the limit. But that's only the first part. The second part is we need to show that every successive term is smaller than the term before it. Because you can see this is true here. Every successive term in the sequence is smaller than the one before it. And so we have to show that that is also true. And we've done that a few times in this class as well. So to do that, what we want to show is that that B sub n, this term, is going to be greater than B sub n plus 1. And so the way to do that would be to take my B sub n, make it greater than 1 over n plus 1 squared plus 3. So again, this should look familiar. We've done this sort of thing before. Now n plus 1 squared, let's just do that over here. That is going to be n squared plus 2n plus 1 plus 3. So we have 1 over n squared plus 3 is greater than 1 over n squared plus 2n plus 4. When we cross multiply, I'm getting kind of low here, we're going to have n squared plus 2n plus 4 is greater than n squared plus 3. Well, I can see that that's going to be true. The n squareds cancel out, and so as n is getting infinitely large, 2n plus 4 is going to be greater than 3. And so, because even just 4 is always greater than 3. So this is true. So what we've shown here is that b sub n is greater than b sub n plus 1. That means that this term here is going to be greater than this term. This term is greater than this term, which is greater than this term. So each successive term is getting smaller and smaller and smaller. That's what we want to show. And so that should make some intuitive sense, because in order for this to converge, two things need to be happening. Each term needs to be getting smaller and smaller, and it has to be converging towards 0, right? If the terms were getting larger and larger, it would not be converging towards 0, and it would not be a converging alternating series. So that is the alternating series test. Two things you need to show. You need to show that b sub n is greater than b sub n plus 1, and you need to show that the limit as n approaches infinity of b sub n is equal to 0. All right, I hope this helps as a little bit of an explanation as to what the alternating series test is. In the next video that I'm going to do, we're going to take a look at absolute convergence. And so absolute convergence means, is this thing going to converge whether it's alternating or not alternating? Because some series may converge only if they're alternating, but not if they are not alternating, or vice versa. So that will be what we'll be looking at in the next video when we get into what is called absolute convergence. All right, see you in class.